So just like we could relate our ionic bonding patterns to the periodic table, we can do the same thing for the covalent bonds. So covalent bonds can form also between unlike atoms. We saw diatomic molecules last time, but now we can expand our repertoire of molecular compounds, or compounds that consist of molecules rather than ions. So our water molecules consist of two hydrogen atoms joined by covalent bonds to the oxygen atom. This is a good example of a compound. Ammonia is another example of a covalent compound. It exists of three hydrogen atoms and one nitrogen atom. Methane would consist of four hydrogen atoms covalently bonded to a carbon atom, and so we've already seen that example as well. So there's many examples of compounds that exist as covalent compounds, and as we move towards talking about biochemistry and the major macromolecules that make up biological systems like proteins and carbohydrates and DNA molecules, these are all going to be built up of very complex molecules that contain lots of different atoms that are bonded together by a variety of interactions. Most of them are going to be covalent bonds, but there will also be some ionic interactions as well. So these are the examples that we gave on the last page. We gave our water example, the ammonia example, and the methane example. So note that all of these guys are sharing their electrons so that each atom that's involved in the bonding pair reaches its noble gas configuration of electrons. So the octet rule is still in play when we're talking about covalent bonds, just like it was when we were talking about ionic bonds. So the number of bonds that are formed to achieve our octet is going to be the same number of electrons that the atom is going to need to reach its octet state. So if we're looking at the periodic table and we're only taking into account the nonmetals, because these are the ones that are going to form the covalent bonds, we can see hydrogen has one electron. It needs one more electron to fill its outer shell. So it's going to create one bond maximum. If we come over to group 3A, boron is in the nonmetal class. Remember, we have our stair steps going down with our metalloids down below. Boron is an exception to the octet rule, and we will talk more about this one. It only has 3 electrons in its outer shell, and so it only has 3 to partner or to pair with another atom. And so it is limited to only forming 3 bonds. So that would give us a total of 6 electrons in its outer shell. And so boron can never actually reach the octet state when it forms covalent bonds. And so it remains a little bit unhappy, but that's what it is for boron, because it only has 3 to offer to sharing partnership. All of the rest of the atoms that are listed here can reach the octet state, or the noble gas configuration of electrons. The group 4 elements have 4 electrons in their valence shell, and so they can make 4 pair bonds with other electrons from other elements, and so to complete their octet for a total of 8 electrons in their outer shell. So they'll make 4 bonds. Carbon will always make 4 bonds. Silicon will always make 4 bonds. Nitrogen has 5 electrons in its outer shell, and so it's got 3 that are unpaired, because remember, if we place the electrons around the outer edge, we go 1, 2, 3, 4, and then we start having to pair the electrons up. And so nitrogen has 3 spaces open to share bonds or share electrons with another atom. And so it can make a total of 3 bonds with other atoms. Oxygen has 6 electrons in its valence shell, and so it has 2 places open where it can make pair bonds. And so it wants to share 2 more to get to 8 electrons. And fluorine, chlorine, bromine, and iodine typically want to share 1 electron pair to get to the octet rule. So one of the things that you'll notice down here with phosphorus and sulfur and chlorine and bromine and iodine is that they have these numbers down here in parentheses as well. And so what this means is because these guys actually start having available d orbitals that are going to be present because from the third shell on, we know that the third shell has d orbitals present, so 3d is present. The elements that are down here, they can kind of expand their valence shell to hold more electrons or more bonds. So phosphorus ideally would like to form 3 bonds to get to its octet state, but it can be coerced into forming 5 bonds by using some of the empty d orbitals to make those extra bonds. And so we'll take an example of both sulfur and both phosphorus to see how these guys can expand. So I'll write those out on paper, and we'll do a review session with those guys. But just note that these guys can kind of expand their orbitals, and they can increase and not follow completely the octet rule. They can follow the octet rule with 3, 2, 1, but they can also get a little bit bigger and not kind of play by that octet rule. So our octet rule overall is a useful guideline, especially for oxygen. You know, oxygen is always going to form 2 bonds. This is something that you can count on. Nitrogen always going to form 3 bonds, something you can count on. Carbon always going to form 4 bonds, something you can count on. Hydrogen always going to form 1 bond. So these are very nice examples, and these are also the elements that are in highest levels in biological systems. And so these are the most common covalent bonds that you're going to see when you're looking at biological organisms. You're going to see carbon-hydrogen bonds, you're going to see carbon-nitrogen bonds, you're going to see carbon-oxygen bonds, you'll see nitrogen-hydrogen, and oxygen-hydrogen bonds, typically in biological systems. Some of the time you'll also see phosphorus and sulfur, and so we're going to use these guys as examples of the expanded orbitals because they also play important roles in biological systems. So phosphorus is a critical component for developing the nucleic acids, so phosphate groups are in there a lot, and sulfur is a component of some of the amino acids to make protein structures from, and among other small molecules that are important for biological functions. So we can see that the octet rule then is our useful guideline, but it does have exceptions. Boron, again, only has 3 valence electrons, so it can only share these and form compounds in which it only has 3 covalent bonds. So it never reaches a complete octet. And then our examples of phosphorus and sulfur can have expanded orbitals, and they can house up to 5 or 6 bonds with other elements. And again, this is going to be because they have vacant d orbitals that can be used as kind of these little side apartments for making extra bonds. And so we'll see how that's possible when we do our review for this section. So let's take a little outbreak here, and we'll talk about how these guys can expand and use these bigger orbitals.